Hi, thank you for visiting our presentation. In this occasion, I would like to present our recent study titled Cascading Earthquake Rupture in a Multiscale Fracture Network with Cascading. The motivation of our work is as follows. From the previous publication, we know that the local stress perturbation in subsurface reservoir that consists of a fracture network or multiple fault segment may induce an earthquake magnitude larger than 5 on a mapped or unmapped fault. For example, the Pohang earthquake, as you can see from the previous study on the right, the Pauni earthquake, and the Prague earthquake. Therefore, we created a hypothesis that's saying that the stress perturbation on well-oriented fracture in a damaged zone might produce a significant earthquake. This motivates us to create the first 3D dynamic rupture simulation among 100 connected multiscale fracture to capturing a cascading earthquake dynamics. The objective of our study is trying to answer the following questions. The first, can large earthquake nucleate on spontaneous cascading rupture on well-oriented fractures in a damaged zone and eventually activating a poorly oriented main fault? Can sizable earthquake cascade in a damaged zone without activating a main fault? And can a co-seismic activation on a fracture in the damaged zone affect the main fault rupture dynamics? For example, the rupture speed. As observed during the Ridgecrest earthquake, where the surface fault of fracture reveal a geometrically complex fault. And we also know that the rupture speed of this event is very low or lower than expected. Therefore, to answer those questions, we conduct a 3D fully dynamic rupture simulation combining 854 fracture embedded with a elastic fault plane. But here we're focusing only on three main model. Model number one is unfavorably oriented fracture and main fault plane. Model number two, favorably oriented fracture and poorly oriented main fault plane. And model number three, favorably oriented main fault plane and poorly oriented fractures. The simulations is dynamically feasible under prerequisite that of analytical multiscale dependence of fracture energy on a fracture size. To have a look in more detail, please visit Garagas et al. With abstract number S51D07. All fractures in the simulation can host a spontaneous dynamic earthquake rupture and are governed by the rapid velocity weakening and rate and state friction law. The fracture size radius distribution follows a power law distribution with radius in the range of 100 to 500 meter. The main fault plane here has length 8 km and width 4 km with depth dependent dip ranges from 40 to 90 degree. And we follow Savage and Brodsky 2011 to distribute the fracture density. And in this study, we consider two dominant strike orientation, north 20 degree and north 120 degree. And then the distribution of this fracture location follows the nearest neighbor method. As I said before, we have 854 fracture plane with a total 49 million tetrahedral element with variable size. And then the fracture plane output from this model is inserted into numerical software SciSol to simulate earthquake dynamics and seismic wave propagation. In this study, we use relative strength of an optimally oriented fault plane that is constrained by R0 or initial pre-stress ratio equal to 0.8. For example, in SH max orientation equal to 65 degree, the background stress loading is mapped into a fracture or fault plane. Each of these fault plane experience different stress loading depends on their geometrical orientation, and they vary from the value 0 to R0 or 0.8. This high R means more optimally oriented, therefore easier to slip, and vice versa. To make it easier, here we plot the lower hemisphere of R distribution. As you can see, the white dot here represent the two fracture families, and the gray dot here represent the least risk fault plane. We vary the maximum horizontal stress orientation from HH max orientation of 40 degree up to 120 degree. However, in this presentation, we only focus on three different orientation or models. F1 is associated with SH max orientation 40, and M2 and M3 is associated with SH max orientation 65 and 120 respectively. The arrow here represent the orientation of horizontal stress. Because we have geometrically complicated model, it will be very tricky to observe the evolution of the rupture and its dynamic interaction. Therefore, we decided to create what we call exploded view. So the exploded view here is essentially the breakdown view of the rupture position multiplied by 3.5 multiplied by its original fracture distance. Note that the original model is on the bottom left of the slide. Let's start it with M1, where the fracture and the main fault plane are unfavorably oriented. So on the left, you see the rupture time, and on the right, you will see the slip evolution of each of individual model. So in this M1, you can see from the rupture time, the slip is very limited to the fracture area inside the nucleation zone, and the rupture cannot propagate onto the neighboring fracture or on the main fault plane. And then next for M2, where the main fault plane is not optimally oriented, but the fracture are favorably oriented. As you can see from the rupture time, as well as the slip evolution, the rupture is started on a subset of a fracture inside the nucleation zone, and then it propagates without triggering a runaway rupture on the main fault plane. This dynamic interaction, the dynamic rupture interaction among fractures, only initiate an R-step rupture on the main fault plane, as you can see from the rupture time here. For the case M3, where now the fracture are poorly oriented and the main fault plane are favorably oriented. As you can see, the rupture start on the main fault plane, and then it propagates bilaterally and activate the off-fault fracture that are directly connected to the main fault plane. And then the dynamic triggering, you can see also when the rupture on the main fault plane reach its edges. One interesting result that we can observe is what we call a cascading speed. The cascading speed is defined as an apparent cascading speed rupture along the fracture network within a fault zone, a fault damage zone. The cascading speed can be obtained by looking at this figure. So for example, the case M2. This figure represents the scattering plot of distance to hypocenter versus the nucleation time of each fracture. Dot exhibit the fracture family number 1, and triangle exhibit the fracture family number 2. The color bar here represent the fracture direction with respect to the north. And the rectangle here is the rupture time contour of the main fault plane only. And from this individual figure, we can already see how rupture develop and activate both fracture families alternatingly in two different directions, in the west and to the east. As you can see from the figure, from the middle figure, the slowest cascading speed occur when the cascading rupture exists in the fracture network without triggering a runway rupture on the main fault plane, as the case of this M2. And interestingly, the cascading speed is comparable to the average rupture speed on the main fault plane for the case of M3. As you can see now from the table, the cascading rupture generates a comparable magnitude to the runway rupture on the main fault plane. As you can see also from the moment tensor solution, the earthquake rupture on the geometrically complicated fault produces low to moderate CLVD moment tensor solution. And now move on to the moment rate function. We can observe the multiple peaks that indicate the cascading earthquake rupture. For example, here when the orientation of SS max is 65 degree. And finally, we have modeled 3D dynamic rupture, earthquake rupture as a cascading over a network of several hundred fractures in a damage zone with or without activation of embedded district fault. And we also observe the dynamic rupture cannot propagate away from the nucleation zone in the case of unfavorably for both fracture and the main fault plane, as the case number 1. And then the dynamic rupture cascading across a well-oriented fracture in the damage zone at low cascading speed generates a comparable a seismic moment release to a runway rupture on the main fault plane, but it fails to dynamically activate a runway on poorly oriented main fault plane. It's only triggered the arrested rupture. And then the main fault activates the off-fault fracture that are directly connected to the main fault plane in the case number 3. And interestingly, this cascading speed is equivalent to the average rupture speed on the main fault plane. And then as an outlook, we want to observe the spectra waveform generated by the case number 1, number 2, and number 3. As you can see from the spectra here, we use we show only 2 stations, and you can see from the spectra, the M2, the cascading rupture generate higher frequency content than runway rupture or M3. This is expected as we have more small-scale heterogeneity on cascading rupture and a multiple dynamic interaction among the fractures. Thank you for your time and attention. Please feel free to contact us if you have questions.